All right, this is going to be a short lecture video on 6.1 inner product length and orthogonality. I'm going to be using this lecture slide. If you want to print it up and follow along, it's up to you. So it's going to be using this one, so I'm just going to switch over now to my Notability. So here we go. So in here we're going to talk about dot product, lengths of vectors, and orthogonality, which in R2 and R3 means perpendicular. So this first part is dot product, and this is a definition, and we're going to define this inner product, also called the dot product, and we write it as a bolded dot. So it's not quite multiplication, and if we can turn around and make U a horizontal vector, you can think of it as a matrix of a 1 by n matrix, and V is an n by 1 matrix, what we end up is getting just a scalar. We get a number. So here's an example. If this is my U and this is my V, U dotted with V, by definition is we take 1 to -3, and we turn around and multiply it by 4 minus 1, 5. And we've already learned we're going to pair up 1 and 4, and then 2 and -1, and then -3 and 5, which is going to give me 4 minus 2 minus 15, so I'm going to get -13. Now if I do it the other way around, V dotted with U, then I'm going to have 4 minus 1 and 5 with 1, 2, and -3, in which case I'm going to have 4 times 1 plus minus 1 times 2 plus 5 times -3, which is going to give me, once again, 4 minus 2 minus 15 equals -13. So I've just demonstrated to you why this property, that if we reverse the order, we get the same answer. Notice when we're dotting, our answer is a number, not a vector. So U dot V is a number. So these other two properties, I will leave it up to you to verify, but I'm going to talk about now this one at the bottom, if we dot a vector with itself. So let's go back to our U vector, and we want to dot U with itself. So 1, 2, -3, dotted with 1, 2, -3. So I'm going to have 1 times 1 plus 2 times 2 plus -3 times -3, which is going to give me 1 plus 4 plus 9, which is 14. So notice here that when I'm dotting U with itself, what I am doing is, I'll get a different color here. Do you see that this is just 1 squared? And this is just 2 squared, and this is -3 squared. And whenever you take any number, whether positive, negative, do you see you're always going to end up with positive number squared is a positive, and a negative number squared is a positive. So do you see whenever you're dotting a vector with itself, you're always going to get either a positive number or 0, and the only way you can get 0 is if every entry is 0. Let's look at U being the 0, 0, 0 vector. So U dotted with itself is going to be 0 squared plus 0 squared, which is going to give me 0. But say I have V is 1 and 0, V dotted with itself is 1 squared plus 0 squared, which is going to give me 1. So do you see the only way when I dot to get 0 is if every entry is 0. Otherwise, if there's one entry, just one entry that's not 0, when I square it, I'm not going to get 0. So the other thing, notice when you're doing these, are you seeing that the first entry gets paired with the first entry? The second entry gets paired with the second entry, and the third entry gets paired with the third entry. So that's one of those things to take into consideration when you're doing these. So now let me talk about length. The length of a vector is if we find, and we write it like this, and it's the double absolute value bars, and this is just the square root of a vector dotted with itself. And I just showed you that a vector dotted with itself, you just square all the entries, and then you just want to take the square root. So now, do you notice if I start with this if I start with this particular one, if I square both sides, the square root cancels on the right. So we could get this one here. So the length of the vector squared is just v dotted with v. So let me go ahead then and let's talk about unit vectors. These are vectors whose lengths are 1. And to find a unit vector in the direction of u, so remember, any scalar multiple of a vector gives you a vector in the same direction. Unless I should say positive scalar, gives you a vector in the same direction as that vector. We've seen this before. So the idea behind this is if I want to get a unit vector in the direction of u, I want to multiply by the reciprocal of the length, and then that'll be the scalar, that's the scalar multiple I want to put in front of u. So let me just show you by example. So for this example, the length of u is just the square root of all the entries squared, so minus 6 squared plus 4 squared plus minus 3 squared. So this is the square root of 36 plus 16 plus 9, which gives me the square root of 61. So a unit vector in the same direction as u is just going to be 1 over square root of 61 in the direction of u. So this is going to give me minus 6 over root 61, 4 over root 61, and minus 3 over root 61. Now let me show to you that the length of this vector is indeed 1. So the length of this vector this is going to be the square root of the first entry squared, the next entry squared, and then the final entry squared. And when I square them, the top gives me 36, and then the squared cancels the square root. 16 over 61, 9 over 61, which is the square root of 61 over 61, which is 1. So I hope you see why this works. So this is how you find a unit vector in the direction of u, is you just multiply by the reciprocal of its length, and you'll get a vector. Here was the vector I got. All right, so that's the next thing. So now we're going to talk about distance between two vectors. So when we talk about distance between two vectors, the idea behind this is if this is my u vector and this is my v vector, you guys have already learned that this vector is v minus u. So what you want to do is you just want to find the length. So the distance is equal to the length of u minus v, u minus v, not v minus u. Yeah, to be honest, it doesn't really matter. U minus v. It's actually, I think u minus v is this way. But since we're squaring, it doesn't really matter which comes first, which one comes second. So if we want to find the distance between these two vectors, we need to figure out what u minus v is. Well, this is 3, 4, minus 7, 6. So I get minus 4, minus 2. So the distance is the length of this resulting vector. So this is the square root of minus 4 squared plus minus 2 squared. So the square root of 16 plus 4, square root of 20. And that's the distance between them. And this really is just the Pythagorean theorem. And I hope you see that it doesn't matter if I did u minus v or v minus u, because do you see the only difference between these is these two signs? And when I square, it doesn't matter. So in this case, it really doesn't matter if I'm doing u minus v or v minus u. So that's how we find distance. All right, and the last thing is another definition, and this is orthogonal. And by definition, two vectors are defined to be orthogonal if their dot products give us 0. So in R2 and R3, orthogonal vectors are perpendicular. And we could actually draw a picture and show that they're perpendicular. But now when you get to like R5, R6, R7, you can't picture it anymore. But the definition will still hold. And so we talk about orthogonal in general for any dimension. So if you want to know if two vectors were orthogonal, you just need to do their dot product. So if we check these two vectors A and B and we do their dot products, all we have to do is multiply corresponding entries and add the results up. Minus 5 times minus 3, so I get minus 16 plus 15, I get negative 1, which is not 0. So these are not orthogonal. They're not perpendicular. Now when I do these two, u dotted with v, this is 12 times 2 plus 3 times negative 3 plus negative 5 times 3, 24 minus 9 minus 15, and I get 0. So yes, orthogonal. These two, if I drew them, I would see that they are indeed perpendicular. So then this last thing is this Pythagorean theorem, and it just says two vectors u and v are orthogonal if and only if, so that means if one side is true, the other side is true. They're either both sides are true or both sides are false. If I add the two vectors and find that length, and I add each individual length squared, I get equals. So let's verify that this is true for these two given vectors u and v. So first let's figure out what their dot products are. So their dot products, just multiply corresponding entries and add the results up. Times minus 4 plus minus 1 times 6. I get minus 14 plus 20 minus 6, which is 0. So orthogonal. Their dot product gives me 0. Now let's check the other stuff. Let's look at the length of u squared. And remember, the length of u has the square root. So if I square it, I'm going to remove the square root. So this is just the entries of u squared added up. So 2 squared minus 5 squared minus 1 squared, which gives me 4, plus 25 plus 1, which is 30. Now let's find the length of v and square that. So this just gives me the entries of v squared and added up. So negative 4 squared, sorry, negative 7 squared, negative 4 squared, 6 squared. So 49 plus 16 plus 36, and I get 101. So now let's figure out what's u plus v. So this is 2 minus 5 minus 1 plus minus 7 minus 4, 6. When I add, I get minus 5 minus 9, 5. Now let's find the length of this new vector, u plus v, and square it. So this is going to be minus 5 squared plus minus 9 squared plus 5 squared, 25 plus 81 plus 25, which is 131. And what we end up here is, if we look at the length of u squared plus the length of v squared, the length of u was 30. So that was 30. The length of v was 101. This is equal to 131, which you see is equal to the length of u plus v squared. The length of u plus, oops, man, I hate when I do that in here. The length of u plus v squared gave me 131. So this holds. This all comes down to, in R2, a squared, b squared, c squared. So it's just the Pythagorean theorem. And this only works when these two are perpendicular. That's when you get the a squared plus b squared equals c squared. So, but we can take this to higher dimensions where we can't picture it anymore. So this is all the stuff for this section, and I hope you were able to follow it.